You learned in the last lesson how the airflow over an aerofoil produces both lift and drag. In this and the following lessons, we shall examine in greater detail lift and the factors affecting it. The aerodynamic forces of both lift and drag depend on the combined effect of many variables, the most important being the airstream velocity v, which when combined with the air density ρ determines dynamic pressure, the formula for which is half ρv squared. This is the common denominator of aerodynamic forces and is a major factor, since the magnitude of a pressure distribution depends on the energy given to the airflow. Kinetic energy equals half the mass times the velocity squared. The shape or profile of the aerofoil and the angle at which the airflow meets it, the angle of attack, together determine the pressure distribution around the aerofoil, and thus the coefficient of lift and drag. The surface area, S, and its condition will also have a direct effect on the amount of lift produced. The larger the surface area for a given pressure differential, the greater the force generated. Compressibility, which only starts to become significant above 300 knots, will be covered in later lessons. Any aerodynamic force can thus be represented as a product of the three major factors, which are the dynamic pressure of the airflow, half ρv squared, or Q, the coefficient of force determined by the relative pressure distribution, that is, the coefficient of lift, Cl, or drag, Cd, and the surface area of the object. The relationship of these three factors is expressed in the equation F equals Q times Cf times S, where F is the aerodynamic force, either lift or drag, Q is the dynamic pressure, half ρv squared, Cf is the coefficient of aerodynamic force, and S is the surface area. Lift is defined as the net force generated normal to, or at right angles to, the relative airflow or flight path of the aircraft. The aerodynamic force of lift is the result of the pressure differential between the upper and lower surfaces of the wing, and for an aircraft to fly straight and level, lift must be constant and balance weight exactly. Several factors will affect the amount of lift generated. First, air density, denoted by the symbol ρ. Next, the aircraft's true airspeed, or TAS, enters the equation as v. The next factor is the coefficient of lift. The final factor is the wing area. Dynamic pressure depends on air density and TAS, and is related to the kinetic energy of the airflow. So the formula is based on half the density and the square of the TAS. Remember that for straight and level flight, lift must remain constant. It is important to remember this formula. L equals half ρv squared times Cl times S. During this examination of the lift formula, we are taking it for clarity that the Cl is determined by angle of attack, which is true, but Cl is also affected by changes in wing shape or profile and some other factors, which are explained in a later lesson. There is a direct relationship between density and the TAS that an aircraft will achieve for a given IAS, usually in connection with a change in altitude, since density decreases as altitude increases. Considering the ICAO standard atmosphere, or EASA, in which the density at 40,000 feet is a quarter of that at mean sea level, we can see the changes in relationship that occur between TAS and IAS because of density change. To maintain constant lift as density decreases, any of the elements of the equation could be changed. But it is impractical to change wing area, and inefficient to change CL from the best lift-drag ratio at 4 degrees angle of attack. So since the dynamic pressure must be maintained, if one element drops, the density, the other, the TAS, must rise, in this case to twice the sea level value. Because of the square function of the TAS, doubling it would increase dynamic pressure by 4, compensating for the 4-fold drop in density. So, since IAS is proportional to the square root of the dynamic pressure, maintaining a constant IAS will maintain constant lift. The lift formula can also be used to look at the relationship between speed and angle of attack at a constant altitude. As before, if one element of the equation is increased, another must be reduced. As speed rises, the CL must be reduced to maintain the same total lift, normally by reducing the angle of attack. If indicated airspeed is doubled, here from 150 knots to 300, the TAS also doubles, increasing dynamic pressure by 4. If dynamic pressure is increasing by a factor of 4, then to maintain lift at a constant, the CL must be reduced by the same factor. In other words, to a quarter of its previous value. By reducing the angle of attack appropriately to keep the aircraft at a constant height. To make this principle easy to understand, we can say that TAS will change in proportion to IAS at a constant altitude. This is, however, not true of speeds above Mach 0.4. The lift formula can be transposed in several ways to calculate variables which may be of interest to a professional aviator. For example, if speed is increased in level flight by 30% from the minimum level flight speed, we can calculate the new CL as a percentage of CL max. L equals half rho V squared times CL times S, when transposed, becomes CL equals L over half rho V squared S. Since density, lift and wing area are constant, this can be written as CL is proportional to 1 over V squared. 30% above can be written as 1.3, so 1 over V squared becomes 1 over 1.3 squared. This equals 1 over 1.69, which is 0.59 or 59%. So, while flying at 30% above minimum level flight speed Vs, the CL will be 59% of CL max. To review what has been covered so far on the subject of lift. Lift must balance weight in straight and level flight, so at any given time, both weight and lift required are constant. To maintain constant lift, if density varies with altitude, a constant IAS must be maintained. With a constant IAS, if altitude increases, density decreases and TAS increases, and vice versa. To maintain constant lift, if speed is changed at constant altitude or density, the angle of attack, or alpha, must be adjusted. If speed is increased, alpha must be decreased. If speed is doubled, alpha must decrease to make CL 1/4 of its previous value. If speed is decreased, alpha must be increased. If speed is halved, alpha must increase to make CL 4 times its previous value. Generally, a cruise speed is derived so that an aircraft operates at its optimum angle of attack, with maximum lift-drag ratio, typically around 4 degrees.